Under the prediction of nuclear cell model, or you can say the independent particle model or single particle model, today we are going to discuss the nuclear magnetic moment and Schmidt model. Actually, the nucleus possesses angular momentum, and corresponding to angular momentum we always define magnetic moment. So our nucleus just behaves like a magnetic dipole possessing a nuclear magnetic moment. So what is the nuclear magnetic moment of a nucleus possessed? We will discuss in this lecture. As you know, a nucleus consists of nucleons, that is protons and neutrons. And in protons and neutrons, proton is a charged particle and neutron is a neutral particle, that is chargeless particle. And these nucleons actually revolve in an orbit inside the nucleus. For simplicity, we will assume here for calculation that our nucleon is moving in circular orbit. But the result obtained for the magnetic moment, considering the orbit as a circle, is not valid only for the circular motion of the nucleon, but it will be valid for any any revolutionary motion of the nucleon inside the nucleus. So first of all, let us consider that a proton whose charge is E and mass is this capital M is moving in a circular orbit. As you know, a circulating electric charge is just equivalent to an electric current, or you can say a current loop. So definitely, due to this circulating positively charged proton, an electric current will be produced. And this electric current produces a magnetic field which you may call nuclear magnetic field. And due to this orbital motion of the proton, it will have orbital angular momentum. And associated with this orbital angular momentum, definitely the proton will have orbital magnetic moment. So you can say simply, due to the orbital motion of the proton, which is a charged particle, it will have magnetic moment. And this magnetic moment can be found by the general definition of a magnetic dipole moment of a current loop. So we consider that the orbit described by this proton is just a current loop, and you have studied in your lower classes that a current loop of any shape and size is just equivalent to a magnetic dipole, and due to that current loop or that magnetic dipole, the magnetic moment is given by this formula. You have studied it in your lower classes physics. So mu in this case is defined as I times A. Here actually I is the electric current and A is area of the circular loop. I have written here area vector, and area is a pseudo vector. So this magnetic moment will be just in the direction of the area vector here. Now, as I have considered that this orbit is circular and its radius is r, so area A will be equal to simply pi r square. Okay? And what will be the current I? As the proton is moving along this circular orbit, and if you consider that the time period of this circular motion is capital T, it means the proton takes T time in completing one revolution, then the electric current will be simply E divided by T, because current is what? This is charge flowing per second. So through any section of this orbit in time t, charge E will flow, so current will be equal to E by T. But what will be T? T is the time taken by the proton in circulating once along this orbit. So in one revolution, you know, the proton will cover a distance 2 pi r. And this distance the proton covers with a constant speed v. So when you will divide this distance 2 pi r by v, you will get the time taken by the proton in one revolution. So T can be written as 2 pi r over v. Okay, I hope you are getting the things. And so this will be simply EV divided by 2 pi r. So electric current is EV by 2 pi r and area is pi r square. So now substitute these two values in the expression for the magnetic dipole moment mu here. So mu will be, so the magnitude of mu will be what? This will be I. I is EV over 2 pi r times A, which is pi r square. So mu is equal to EV divided by 2 pi r into pi r square. Now this pi will cancel out, one of the r will also cancel out. So the magnitude of magnetic moment, this is EV r by 2. This is actually the orbital magnetic moment, you know, because this is due to the orbital motion of the proton. Now this expression for the magnitude of magnetic moment of proton can be written in vector form. If you want to write it in vector form, you can write mu is equal to E over 2 times r cross v. R cross v. Now let us multiply this expression by m and also divide it by m. So the result remains same, where m is actually the mass of the proton. Okay. Now you can write it E over 2m times r cross mv, because m is a scalar, so you may associate this m with v. But what is this mv? mv is simply the linear momentum p of the proton. So mu can be written as E over 2m times r cross p. But you know, r cross p is the orbital angular momentum L. So r cross p has been replaced by L. So mu is equal to E over 2m times L. In fact, here I have not written the statistical weight or the nuclear G factor, because if you want to generalize this result, you should write it mu equal to E over 2m times GL times L, where GL is actually known as the orbital G factor. But the value of this orbital G factor is equal to 1, so it has been not written here. Okay, but when this G factor will be not equal to 1, then we have to write this factor GL in the expression of this magnetic moment. Now you know, this is the orbital magnetic moment due to the motion of a single proton, only one proton. But as you know, neutron is revolving in the circular orbit or any type of orbit inside the nucleus in the similar manner as the proton revolves. But this type of magnetic moment you cannot associate with the motion of the neutron. Why? Because neutron is has not any charge. So if you will write such expression for neutron, you have to write E equal to 0, and you can see if E is equal to 0, mu will be equal to 0. So in fact, this orbital magnetic moment for neutron will be simply 0. And reason is what? Reason is that neutron has no charge. So due to this orbital motion, only the proton has magnetic moment, not neutron. Okay, I think you have understand the fact. Now, you have studied in quantum mechanics that the eigenvalue of this L is equal to root over L into L plus 1 times h bar. Okay, where L is actually called the orbital quantum number, and since this L is in case of nucleons, this L is very large, so this 1 is simply neglected, and you may write an approximate formula for this L in this case. And this, when this 1 will be neglected in comparison to L, this will be simply a square root of L square into h bar. So this is simply h bar L. So in this case, we will write the magnitude of this vector L simply by h bar L. Okay? And therefore, when you will substitute this value of L in this equation, you can see in equation 1, instead of L, now we will write simply h bar L. Then what will be the expression for the magnetic moment? This will be, you can see, mu equal to EH bar over 2m into L. Okay, I have written it in the vector form. As I have told you earlier that this result we have found by considering a circular orbit, that is, we have assumed that the proton is revolving in a circular orbit, but this result is valid not only for the circular orbit, but it will hold for non-circular motion too. So this is just a general result, you can say. Now you can see EH bar over 2m. This is a constant factor. And this EH bar over 2m, this is known as nuclear magneton. And this nuclear magneton is used just as a unit, natural unit, to measure the nuclear magnetic moment. And so, if you want to write the value of nuclear magnetic moment, you may use this EH bar by 2m as unit, and this is denoted by the symbol mu n. Okay, and you can remember the value of this nuclear magnetic moment. Mu n is equal to EH bar over 2m, and when you will substitute the numerical values of all these quantities, because you know the charge of proton is 1.6 into 10 to the power minus 19 coulomb, you can write the value of h bar and mass of proton, and after simplification you will get that this nuclear magneton is equal to 5.05 into 10 to the power minus 27 ampere meter square, or its unit may be written as Joule Tesla inverse, T for Tesla, J for Joule. This is Joule Tesla inverse. So remember this value of the nuclear magneton, and this is just a unit to express the value of the nuclear magnetic moment. Okay, and as I have told you that neutron will not have this type of magnetic moment, because neutron has no charge. As you can see, I have calculated the magnetic moment associated with the orbital motion of the proton, considering only one proton revolving inside the nucleus. But in general, inside a nucleus, there may be a large number of protons revolving in similar manner. So if you now consider a nucleus which has Z protons, it means the proton number of this nucleus is Z, then the orbital magnetic moment of this nucleus will be what? We will simply calculate the magnetic moment of each and every proton, and then we will add them simply vectorially. And when you will find the vector sum of the magnetic momenta of each and every proton, then you will get actually the orbital magnetic moment of the nucleus. So the orbital magnetic moment of the nucleus, that is mu orbital, will be what? This will be equal to EH bar over 2m times summation over k 1 to z Lk. In fact, here k runs from 1 to z. So this is simply L1 plus L2 plus L3 plus Lz. So when we will add vectorially the magnetic moment due to the orbital motion of every proton, then we get the magnetic moment due to the orbital motion of the proton. So this equation 3 represents the orbital magnetic moment of a nucleus containing Z protons. Okay, this is just a simple calculation. And as I have told you earlier that neutrons are chargeless, and so they do not contribute in the orbital magnetic moment. Okay. Now, apart from this orbital magnetic moment, the nucleons have also some intrinsic spin angular magnetic moment, because you know the nucleons have intrinsic or spin angular momentum along with the orbital angular momentum, and so associated with the spin angular momentum, these nucleons have a spin magnetic moment too. And this spin is associated not only with the proton, but you know both protons and neutrons are spin half particles. So due to the spin of the nucleons, both protons and neutrons will have a spin magnetic moment. Neutron will have a spin magnetic moment, and proton will have a spin magnetic moment, and at the same time neutron will also have a spin magnetic moment, because neutron also possesses a spin angular momentum. Although you have seen that the orbital magnetic moment of neutron is 0, but the spin magnetic moment of neutron will be not 0, because this intrinsic spin angular momentum is also in neutron, just like proton. So neutron has also intrinsic spin magnetic moment. So if you want to find the total spin magnetic moment of a nucleus, what you will do? We will simply add vectorially the spin magnetic moment of all protons and all neutrons. All protons and all neutrons. So let us see that mu spin, it means this is actually the spin magnetic moment of a nucleus. What will be this? You have seen the expression for the mu orbital. See the expression for mu orbital. This is the expression for mu orbital. We will just write same expression for mu spin, but instead of this Lk, now we will have to write the spin angular momentum Sk. But spin angular momentum is in both proton and neutron, so we have to write the term for proton and neutron too. But as I have told you earlier that the nuclear G factor for orbital motion, that is GL, is equal to 1. So we have not written here GL. But in case of a spin angular momentum, the spin G factor is not equal to 1. So you have to write the factor, that is G factor for the nuclear spin. So the expression for mu spin will be what? EH bar over 2m will be a common factor, and first of all we will write the term for the spin magnetic moment due to the proton. So I have written here Gp, which is actually the nuclear G factor for proton, and summation over k1 to z Sk. Sk is what? This is the spin angular momentum of kth proton, and when you will sum up these all spins of the all protons, you will get the total spin magnetic moment of all protons. And then we will add the spin magnetic moment due to the neutrons. And for neutron, I have written here the G factor by the symbol Gn. This Gn is what? This is nuclear G factor for neutrons. And similarly, the spin angular momentum of neutron has been also written here Sk, which is for kth neutron. But remember, as the nucleus possesses Z protons and let us say a total number of nucleons, then the number of neutron will be a minus z. So here the limit will be z plus 1 to a. A is actually the total number of nucleons, or you may call it mass number of the nucleus. Okay. So here the limits runs from z plus 1 to a. Okay. So this equation 4 defines the spin magnetic moment of a nucleus. So you have seen that our nucleus has two types of magnetic moment. First one is called mu orbital, which is due to the orbital motion of all the protons inside the nucleus. And another is intrinsic magnetic moment, which is due to the spin of the nucleons, and that I have denoted by the symbol mu spin. So if you now want to find the total magnetic moment of the nucleus, what will be that? That will be simply the resultant of mu orbital and mu spin. And to get the resultant of these two vectors, we have simply add vectorially mu orbital and mu spin. So when we will add vectorially mu orbital and mu spin, then we will get actually the magnetic moment of our nucleus. So magnetic moment of nucleus, which I have denoted by the symbol mu nucleus, will be equal to what? This will be mu orbital plus mu spin. Now you have seen the expression for mu orbital and mu spin. So now we will simply substitute the values of mu orbital and mu spin to get the total magnetic moment of the nucleus. You can see this expression will be what? Mu nucleus will be equal to mu orbital. Mu orbital, when you consider the magnetic moment due to proton, this will be what? Eh bar over 2m will be a common factor, and in case of proton, you write two types of angular momenta. This is summation over k 1 to z Lk. This represents actually the orbital magnetic moment due to the protons, and plus Gpsk. Summation is for both. This is the spin magnetic moment due to the proton. So this first term represents the total magnetic moment due to protons. In protons contribution, you can see there are two contributions. First one is due to the orbital motion of the proton, and second due to spin of the proton. But in case of neutron, you know there is no magnetic moment due to its orbital motion. Only due to the spin, the neutron has magnetic moment, and so for neutrons, we write the term Gn summation over k z plus 1 to a sk. Okay, so simply we have here added the both angular momenta, and then we obtain the both you can say magnetic moment, and then you obtain the total magnetic moment mu nucleus. Okay. In fact, these calculations have been made on classical basis, because when you talk about a definite trajectory of proton, it means you are considering the classical physics. But at the same time, we have also considered a spin, which is purely a quantum mechanical concept. But if you want to write the quantum mechanical expression for the magnetic moment mu, then how we can write that expression? Actually, the quantum mechanical expression for magnetic moment mu can be obtained simply by taking the expectation value in the state of the nucleons defined by psi n r1 r2 so on ra. Psi n is for nucleus or nucleons, you can say, and r1 r2 these actually represents the position of the different nucleons. Okay, as our nucleus has total number of nucleons equal to a, so this r will have in fact a values r1 r2 so on ra. Now the magnetic moment defined in equation 5, this will be just taken as an operator. This is just magnetic moment operator. And if you want to find the expectation value of any operator in integral form, how you define? If this function is actually normalized. So in case of normalized wave function or the eigenstate, the expectation value is how defined? You know, if you want to find the expectation value of any operator, let us say a, then this is defined as integral psi star a psi d tau, or you may write d3r. This is just a way to find the expectation value when the wave function psi is actually normalized. So in this case, at the place of this a, operator a, we will write mu nucleus, and mu nucleus is equal to this much, as you can see in equation 5. So considering this mu nucleus as an operator, the quantum mechanical expression for the expectation value of this operator mu nucleus in this state psi n r1 r2 rn and ra will be what? This mu will be equal to, since eh bar by 2m is a constant factor, so I have taken it outside of the operator, and psi star, so this will be psi n star r1 r2 to up to ra, and at the place of the operator now we will write this much. You can see, in fact, this factor eh bar over 2m is associated with this operator, but since it is constant factor, so it has been taken outside of the integral. And this is summation over k 1 to z lk plus gp sk plus gn summation over k z plus 1 to a sk, and again psi, so this is psi n r1 r2 ra, and since this psi n is a function of a independent variable, so I have written here the volume element like this, d3r1 d3r2 so on d3ra. So this equation 6 is simply the quantum mechanical expression for the magnetic moment of a nucleus, which represents simply the expectation value of this mu in the state psi n r1 r2 so on ra. Okay. Now we have studied the single particle model in cell model or the independent particle model, and you have seen in single particle model the magnetic moment is entirely due to a single odd nucleon, that may be a proton or a neutron, and that odd neutron or proton is actually responsible for the magnetic moment. Okay, so in this case we consider a nucleus which will be either even z or odd n. It means the nucleus has a proton number which is even and a neutron number which is odd. Or we consider the odd Z and even n nucleus. So, sorry, there is some problem here, but this problem will be removed shortly. You can see. Yes. Now see this. So, in single particle model, as I have told you, that the in total magnetic moment is due to only the odd nucleon. And so in this case, we consider either an even Z and odd n nucleus or odd Z even n nucleus. We consider it. So in this case, what happens actually? In fact, in this condition, the orbital and spin angular momenta of all other nucleons will cancel in pairs. For example, if you consider that Z is equal to 7 and n is equal to 8. Let us consider. Then what will happen? In fact, this 7, there will be 7 pairs and only one nucleon will remain unpaired. That one nucleon will be responsible for the magnetic moment. All the paired nucleons have actually total angular momentum equal to 0, because the magnetic moment of one nucleon will cancel the other. So the magnetic moment which remains non-zero, that is only due to the unpaired nucleon. Okay. And this concept is actually known as a Schmidt model. When you say that the orbital and spin angular momenta of all paired nucleons cancel and the magnetic moment is only due to the unpaired nucleon, this model is called a Schmidt model. So now we will discuss this Schmidt model in detail. Okay. So I have written in heading the magnetic moment of nucleus and a Schmidt model. Okay. Now let us consider L is the orbital angular momentum of the odd nucleon. Okay. And S is the spin angular momentum of the odd nucleon. We are not talking now about the paired nucleon. Only you have to consider now the odd nucleon in case of the even Z and odd n nucleus or odd Z and even n nucleus. You have to consider only one nucleon which is unpaired, which is odd. Okay. Now you know that the total nuclear spin or total angular momentum. When you say nuclear spin, that means total angular momentum, which is denoted by the symbol J. This will be equal to L plus S. When you will add the orbital angular momentum of the odd nucleon and the spin angular momentum of the odd nucleon, you will get the total angular momentum of the odd nucleon. And that total angular momentum, which I have denoted by the symbol J, is also called nuclear spin. So nuclear spin J is equal to L plus S. Okay. Now the magnetic moment associated with this L and S we have already defined earlier. So you can see that the magnetic moment associated with the orbital angular momentum mu L is given as GL times L. Here actually the expression should be GL into H bar L, and for mu S this should be GS into H bar S. But here H bar has been taken as a unit, so I have not written here H bar. Remember, this H bar is a constant factor, so we can take its value arbitrarily 1, and we do not take this h bar into our calculation. So for simplicity, this h bar has been taken as unity, and the expression for mu L we write simply GL into L, and for mu S we write GS into S. Okay. Now you can see, due to the odd nucleon, our nucleus has orbital magnetic moment mu L and a spin magnetic moment mu S. So the total magnetic moment of our nucleus will be what? That total magnetic moment will be simply the vector sum of mu L and mu S. That is the resultant of mu L and mu S. So the resulting magnetic moment of the nucleus, which is only due to the odd nucleon according to the single particle model or the independent particle model, that will be equal to what? Mu equal to mu L plus mu S. Now substitute the value of mu L and mu S. You can write mu is equal to GL times L plus GS times S. Okay. Now if you want to find the magnitude of this total magnetic moment mu, how you can find? There is a simple technique to find the magnitude of this resultant magnetic moment mu. See here, in this triangle I have actually denoted the vectors L, S and J. As you know, J is equal to L plus S. J is equal to L plus S. Okay. So according to triangle of addition, if you represent this L vector by this line, suppose that PQ, and S vector by this QR, then according to triangle of addition, this line PR will represent the vector J. This is just the triangle of addition of vectors. Now suppose the angle between vector L and vector J is alpha, and angle between vector S and vector J is beta. So this angle will be beta and this angle is alpha. Now since you know that this mu is equal to GL times L plus GS times S, GL and GS are simply numbers, that is scalars. So if you want to find the magnitude of mu, you may follow a simple technique. You have to take the component of this vector L along this mu, and mu is parallel to in fact J. You have seen earlier, mu is parallel to J. So you can say that the magnitude of mu can be found in this manner: GL times component of L along J plus GS times component of S along J. Okay. Now see, L vector makes an angle alpha with J. So what will be the component of this vector L along J? This will be simply modulus of L times cos alpha. Modulus of L times cos alpha. So component of L along J, this will be what? This will be modulus of L times cos alpha, and modulus of L is what? This is a square root of L into L plus 1 into h bar, but I have not written here h bar. Remember, actually the eigenvalue of the orbital angular momentum operator, this is root over L into L plus 1 into h bar. But we have written here only root over L into L plus 1 h bar, that is we have omitted h bar. Why? Because I have told you earlier that this h bar, which is a constant factor, has been taken unity. So I have not written here h bar. Okay. And cos alpha plus GS times component of S along J. Component of S along J. And what will be the component of S along J? This will be simply equal to modulus of S times cos beta. Why cos beta? Because this S vector makes an angle beta with J. Now the magnitude of this S, this is a square root of S into S plus 1 into H bar. Again H bar has been taken unity, that is taken 1. So this is simply GS times root over S into S plus 1 into cos beta. Okay. Now what will be the value of cos alpha and cos beta? You may find it by the properties of triangle. You have studied in trigonometry the properties of triangle, and from that that concept you can find the value of cos alpha and cos beta. Now see, alpha is the angle between the sides PQ and PR of this triangle. So according to triangle properties of triangle, what will be this cos alpha? This cos alpha is equal to what? This will be PR square plus PQ square minus QR square divided by 2PQR. But this PR, PQ and P and QR are actually the magnitude of J, L and S. So this cos alpha from the properties of triangle is written as mod of J square plus mod of L square minus mod of S square over 2 times mod of J into mod of L and plus GS times root over S into S plus 1, and then there is cos beta. Again you can see this angle is beta, so from properties of triangle cos beta will be what? This will be simply mod of J square plus mod of S square minus mod of L square over 2 times mod of J into mod of S. I hope you have an idea of this formula for finding the angle between two sides of a triangle. Okay. Now see, the modulus of J and modulus of L, we will write expression for this. So in this expression will be what? Mu equal to GL into root over J root over L into L plus 1. And you can see there is mod of J square. As you know, the mod of J is equal to what? This is equal to root over J into J plus 1 into H bar. But H bar has been taken unity. So this mod of J square will be simply equal to J into J plus 1. Mod of L square will be L into L plus 1. Mod of S square will be S into S plus 1. Okay. So in similar manner, in the denominator you can again write for expression for mod of J and mod of L. So writing these expressions, what will be your result? You can see mu will be equal to GL times root over L into L plus 1, and instead of mod of J square I have written here J into J plus 1. Instead of mod of L square I have written here L into L plus 1, and instead of S mod of S square I have written here S into S plus 1, and in denominator there was mod of J into mod of L, and that will be root over J into J plus 1 times root over L into L plus 1. And the similar manner, in second term you can see there is GS into root over S into S plus 1, and here there was actually mod of J square, so I have written this much, and instead of mod of S square I have written this, and instead of mod of L square I have written this, and in denominator there was 2 mod J mod L, mod J not L, but there will be mod S. Here is I have written it making a mistake, so this will be what? This will be actually root over S into S plus 1. Okay. So you can see there is in fact mod of S, and that mod of S will be equal to root over s into s plus 1. Now you can see this root over L into L plus 1 and this root over L into L plus 1 will cancel out. Similarly, this and this will cancel out. And what will be our result? You can now see. See this. This will be simply j into j plus 1 plus L into L plus 1 minus s into s plus 1 over 2 root over j into j plus 1 times gl. Gl remains here, so I have written here gl. And similarly, this in second term, there will be j into j plus 1 plus s into s plus 1 minus L into L plus 1 over this much into gs. Okay, so this is the magnitude of the magnetic moment of our nucleus. Now you know this expression is only for the odd nucleon according to the single particle model. Although the nucleus possesses a large number of nucleons, but the magnetic moment due to the paired nucleon is 0. Only one nucleon contribute this magnetic moment, and that is actually the unpaired nucleon. Okay, so although the nucleus has a large number of nucleons, but we are considering this magnetic moment only due to one nucleon. So we can say that this is just a single particle model. And for a single particle, you know, the spin s will be equal to 1 by 2. That may be either a proton or a neutron. For both, spin s is equal to 1 by 2. Now, apart from this, we will have actually two cases. The two angular momenta, that is L and S. These two momenta may be in same direction, that is both L and S may be parallel to one another, or these L and S may be anti-parallel to one another. So there are two possibilities, and in both possibilities, what will be the value of mu? Now we will calculate it. You can see here. In first case, we consider L is parallel to S. L and S both are in same direction. Actually, when L is parallel to S, that is called actually a stretch case. That is called a stretch case. In this condition, you know, since L is parallel to S, so the nuclear spin, which is denoted by the symbol I or J, I have written here I. This I represents the nuclear spin, or you can also write it equal to J, and that is equal to L plus S when L is parallel to S. And since you know for a single nucleon, either proton or neutron, S is equal to half, so this will be simply L plus half. So J or I will be equal to L plus half when we consider the stretch case. Okay, and so you can also say that this L will be equal to I minus 1 by 2 or J minus 1 by 2. Okay, the another case is when L is anti-parallel to S. When L is anti-parallel to S, this is called jackknife case. L anti-parallel to S, this is called jackknife case. And in this condition, the nuclear spin, which I have denoted by the symbol I or J, that will be equal to L minus S. But S is half, so this will be L minus half. And if you find the value of L in terms of I or J, that will be I plus half. Or you may also call it, this is equal to J plus half. So now you can see in this expression 8, if we want to find the expression for this mu in these two cases in terms of I or J, what we will do? Instead of S, everywhere we will write 1 by 2. Instead of S, we will write 1 by 2. And if you want to express this L in terms of J or I, then you will write L equal to I plus minus 1 by 2. plus sign will be in case of jackknife case and minus in case of stretch case. So what we will do, I have not done the algebra, you can do it yourself. I am just giving you a hint. In all terms, replace s by 1 by 2. In first step, what we have to do? S will be replaced by 1 by 2. And L will be replaced by I minus 1 by 2 if the case is of a stretch case. And this L will be replaced by I plus 1 by 2 if we are considering jackknife case. Okay? So after making these substitutions in this equation 8, you will get actually the value of mu in terms of I or in terms of j. Okay? L has been replaced in terms of I. S has a fixed value 1 by 2. So the final result for mu will be in terms of either j or in terms of I. J and I both are same. I have not done the algebra. There will be a lot of algebra of addition, subtraction, multiplication, and this is just a very little concept, so you can do it. So doing all those algebra, we will find that mu is equal to I minus half into GL plus 1 over 2 GS for the stretch case. It means this result you will obtain when you will use that L is equal to I minus half. Then you will get this result. Okay? And when you will write L equal to I plus half, that is in case of jackknife case, making all those algebra, you will get that mu is equal to I over I plus 1 times I plus 3 by 2 GL minus 1 by 2 GS. So I have written these expressions directly here. You can do the algebra as I have given you the hints. Replace in all terms s equal to 1 by 2, and when you want to find the value of mu in a stretch case, replace this L by I minus 1 by 2, and when you want to find the expression for mu in jackknife case, you replace L by what? I plus 1 by 2. Instead of I, you can write in fact j, and j will be, when you write I, it means you have to replace that j by I. In this expression I have written j, but this j will be now replaced by I. Okay? So after doing these algebra, we will have these two results, which I have written here directly, but you can do this yourself. Okay? Now see, we have two relations which defines the magnetic moment of a nucleus in two cases. In first case is a stretch case and another case is jackknife case. And in both of these results you can see that the magnetic moment mu depends on the nuclear spin or the total nuclear magnetic moment I or j. It means mu is a function of I or mu is a function of j in both cases. So we can plot a graph between mu and I on the basis of these equations 9 and 10. Okay? And when you will plot a graph, you will get actually the curve, and those curves are actually known as a Schmidt curve. So I have mentioned here that these relations define two curves for mu versus I with the values I equal to L plus minus 1 by 2. When you write I, so I means in fact j. You can write j equivalently for each class of odd even nucleus. The values of mu are known as a Schmidt value, and the curves are known as Schmidt lines. Okay? Now, What are the values of this G factor, GL and GS? GL and GS, what are the values? In fact, the values of GL and GS for a single nucleon have been found experimentally, and you have to remember these values. In fact, for protons, it is found from experiment that GL is equal to 1 and GS is equal to 5.58. You have to remember these values. Okay, these are actually experimental values. And for neutrons, it is found that GL is equal to 0 and GS is equal to minus 3.82. Okay. Now, if we will substitute these values of GL and GS in those two equations 9 and 10 separately for proton and neutron, then actually we will have four expressions. Two equations for proton and two equations for odd neutron, because there are two cases, a stretch case and another is jackknife case. So for odd proton, if you want to write the expression for mu, then in a stretch case we will substitute the value of GL and GS for proton. You have seen GL is equal to 1 for proton, and what is the value of GS? You can see GS is 5.58. Okay, so substituting GL equal to 1 and GS equal to 5.58 in this equation 9, we will get the expression for the magnetic moment of the odd proton in a stretch case. Okay, and when we will again substitute the value of GL and GS for proton, that is GL equal to 1 and GS equal to 5.58 in the another equation, then again we will get the expression for mu. I have again not simplified that expression. You can do this algebra again, and when you will do the algebra, you will find that in a stretch case, that is when I is equal to L plus half, I or J you can say, J equal to I, you can say. When it is L plus half, that is you are considering the stretch case. Then substituting the values of GL and GS for proton, we get mu equal to I plus 2.21. You can see this is just a equation of a straight line. Mu equal to I plus 2.29. This is just equation of a straight line. In fact, this straight line has an intercept on y-axis equal to 2.29. And similarly, when you will put the value of GL, which is 1, and GS, which is 5.58 for proton in the second case, then you get the value of mu, which is equal to I minus 2.29 I divided by I plus 1, and this will be obtained in the second case, that is jackknife case, when J or I is equal to L minus half. And in the similar manner, when you will substitute the values of GL and GS for neutrons in those two equations, then again for those two cases you will have the value of mu for odd neutron. Mu will be equal to, in fact, minus 1.91 I in a stretch case, and mu will be equal to 1.91 I over I plus 1 in jackknife case. So you can see, corresponding to these values of proton, GL and GS for proton and neutron, now we have actually four equations for mu. Two equations for proton and two equations for neutron. So if you will plot a graph of mu in against of I, then we will have actually two curves for proton and two curves for neutron separately. When then our nucleus is uh, odd Z nucleus, odd Z, and even N, then we will plot mu in against of I on the basis of this equation 11, and when our nucleus will be even Z and odd N, then we will plot mu in against of I or J on the basis of this equation 12. And in both cases we will have actually two curves. Okay. Now see what type of curves will be obtained. I have shown here in this figure. Actually, you can see that the magnetic moments obtained on the Schmidt model for odd Z and even N. See here, odd Z means odd P and even N, Then the curves obtained have been shown in this figure. Okay. In fact, in this figure you can see there are actually two lines, and these two lines are for I equal to L plus 2. This line you can see here, this line which is obtained after plotting this mu in against of J or I. I have written the values of this spin on the x-axis and the value of magnetic moment on the y-axis. Here magnetic moment mu has been measured in units of nuclear Nm. What does this abbreviation means? Nm means nuclear magneton. So in unit of nuclear magneton, the value of magnetic moment have been written on this y-axis, and nuclear spin, that is I or J, have been written on x-axis. You can see here. And this equation, in this figure, the two curves have been obtained for the odd P nucleus and even N nucleus. Odd P means number of proton is odd and the number of neutron is even. So you can see for I equal to J equal to L plus 2, we will have this curve or this straight line. This is just a straight line. And for I equal to J equal to L minus 2, we have this line or this curve. This is actually a Schmidt line. Okay. Now these lines, as you know, are known as a Schmidt line, and it is remarkable that the experimentally measured value lie between these two lines, except for a few light nuclei, and particularly there is a nucleus NP whose mass number is 237. That nucleus actually does not follow this Schmidt curve. It means the magnetic moment of this nucleus is not between these two lines. All other nuclei, except some lighter nucleus, we will have actually the magnetic moment lying between these two lines. Only exceptions are what? Lighter nuclei, and in case of heavier nuclei, this NP, which has a mass number of 237, that does whose magnetic moment does not lie between these two Schmidt lines. Now, similarly, you can see if we plot a graph of mu in against of J for a nucleus which have actually even P but odd N, then the curves obtained are shown in this figure. You can see here again we have plotted mu in against of I or J, and these curves are obtained for the nuclei with even Z or even P and odd N It means here the magnetic moment is due to the odd neutron, and in first case that was due to the odd proton. Okay. Now you can see that nuclei roughly fall into two groups. One set of nuclei is close to the Schmidt line, which is in fact J equal to L plus half. In both of the figures you can see J equal to L plus half. And the other set is close to the line J equal to L minus half. You can see this figure. In fact, this is a small circle denotes the nuclei for which is closer to J equal to L plus half, and this cross denotes the nuclei which is closer to J equal to L minus half. Cross is for J equal to L minus half, and this circle is for J equal to L plus half. So see this figure. In fact, the experimental points belonging to this cell model configuration with J equal to L plus half are marked by circles, as I have told you, and they are mostly found to be close to the Schmidt line J equal to L plus half. As you can see, this is a line for which J equal to L plus half, and these circles are close to this line J equal to L plus half. And the other experimental points marked by this cross, you can see here, marked by these cross edge. These points are actually close to the line J equal to L minus half. I am showing here the figure which is for odd proton and even n, but same fact is valid for the other figure. You can see it here. Okay. You can see for J equal to L minus half, these cross are very close. So the nuclei with J equal to L minus half is closer to the Schmidt line for which J equal to L minus half. And these nuclei which has been represented by this circle, that is closer to J equal to L plus half. Okay. So I am just showing because both figures are in 2 pages, so I am showing it. I am showing you only one page, but the fact which I will talk about, that will be for both of the figures. So you can see that since these there is actually some deviation from the Schmidt line values, and that deviation actually depends on the odd number of proton or odd number of neutron, not on the odd number of particle P or N. Okay. In fact, the deviation from the Schmidt line indicate that the single particle model is only of limited validity, as the experimental value slightly deviates from this theoretical value. So this model is not 100% correct, you can say. Its validity is limited. In fact, why its validity is limited, there are some important reasons behind this, and you can talk about those reasons why there is a deviation of the theoretical value of mu and the experimental value of mu. The theoretical value which we have obtained here on the basis of the single particle model, that value actually differs slightly from the experimental value. And what are the reasons behind this? You can see this. Actually, there is no reason why the nuclear potential should always be spherically symmetric as assumed in the single particle model or in the independent particle model. So these values will be valid only when you consider that the nuclear potential is spherically symmetric. But if you will consider that our nucleus is not that our potential is not spherically symmetric. It means you are talking about the deformed nucleus. In that case, there will be uh, a nucleus which will be either spheroid or ellipsoid. So when we will consider the spheroid nucleus or ellipsoid nucleus and then make calculation, then the value obtained will be actually very close to the experimental value. So our consideration of the spherical nucleus is one of the important reasons behind this deviation of experimental value and the theoretical value. The another reason you may say that the extreme independent particle motion is not realistic. As in this model, we consider the extreme independent particle motion, and that motion is actually not realistic. In fact, this motion is perturbed by the presence of other nucleons due to the uh, residual interaction and the results in of the configuration mixing. Okay, and also one has to include the effects of the collective motion in this study. Then actually there will be a little deviation. Okay. We can also say that in calculating the magnetic moment of these nucleons, we have used the free nucleon magnetic moments, and it is likely that the meson clouds around the nucleons in the nucleus are affected by the presence of the other nucleons, representing in the quenching of the nucleons intrinsic magnetic moment. So these are the reasons why the experimental value of mu predicted by this independent particle model or single particle model and the experimental value are slightly deviated. So I hope you have understand this these calculations of magnetic moment of a nucleus and the Schmidt model. And so if you will watch this video seriously, you will get the things very easily, and everything will be in your mind. And this is actually a very important concept for your different type of examinations. So watch the video seriously, write down in your notebook, and then you will enjoy it.